If you haven't done so yet, please pause the video and try to solve the question before listening on. It turns out that because we have a collision between the bullet and the rod, we can conserve angular momentum. And that can be written as L sub I is equal to L sub F, which stands for initial angular momentum equaling the final angular momentum. Now, initially, the only object that's moving in the system is the bullet, so it will be the only object that has angular momentum. So let's fill in the expression for the angular momentum of the bullet. So in this expression, we have r, which is the position vector of the bullet with respect to the axis of rotation. We'll talk about that more in just a second. M would be the mass of the bullet, v would be its speed, and then theta is going to be the angle between the velocity vector and that position vector. Now, let's look at the bullet right before it hits the rod, so it would be located perhaps about right there. And at that location, we could draw a position vector originating from the axis, which would essentially point horizontally to the right. So that would be the position vector, and maybe we could terminate it right there because we want to take a look at the velocity vector. And the velocity vector is pointing off in this direction right here. And since this angle is given as 60 degrees, we know that this angle right here also is 60 degrees, making this angle here 120 degrees. So we can see from this drawing that the angle between the velocity and the position vector is going to be 120 degrees. That's what we'll be substituting in for the theta of the equation. The speed is unknown to us. The mass was given, and then r would be the length of this position vector. And since the rod was 0.5 meters long, this position vector would have a length of 0.25 meters. So that's what we'll be plugging in for r. Now, after the collision, the rod and bullet will be sort of moving together, so there's going to be some final angular momentum. We would want to note after the collision, the total rotational inertia is going to equal the rotational inertia of the rod plus the rotational inertia of the bullet. Now, when a rod spins about this central axis that's shown in the picture, we could look up the moment of inertia in that situation for that rod. And it turns out to be m times the length squared divided by 12. There should be a table in the chapter of your textbook that gives the different rotational inertias of objects depending on the axis that they're rotating about. So this value would have to be looked up in the textbook. And then the bullet can be treated as a particle, and the rotational inertia of a particle can be the mass of that particle times its radius squared. The radius, again, being that distance from the particle to the axis of rotation. So this total expression right here represents the total rotational inertia of the system after the collision. So when we plug into the final angular momentum, which is the rotational inertia multiplied by the angular speed, we can use this expression in brackets for that rotational inertia I. So let's substitute it in. So now that the equation is fully set up and we're trying to solve for v, we can divide both sides of the equation by rm sine theta. We could then plug in all the known values. Remember that capital M was the mass of the rod, which was given as 4 kilograms. L is the length, which is 0.5 meters. R is the length from the axis of rotation to where the bullet is being lodged, and that would be 0.25 meters. Lowercase m is the mass of the bullet. Don't forget to convert that into kilograms. We've noted that theta was 120. The angular speed is given as 10. And so now we're ready to plug everything in. And when you crunch that all down, you should get approximately 1.3 times 10 to the 3. And then the unit will be meters per second since we used all standard units for our numbers. This is the correct answer to the question. Thanks for watching the video. If you liked it, please click the thumbs up icon and subscribe to the channel so you could stay tuned for additional videos. You're welcome to send in your own question to the email address on the screen, and I'll do my best to post an answer to it.